equation is that we can study all those systems with the help of that mathematical equation. We can plot graphs, we can find frequencies, we can find time periods of such systems, because we know how their frequency, how their acceleration is varying with displacement. One last thing that we discussed was how displacement of a system undergoing a simple harmonic oscillator varies in time, and I discussed two different graphs for it. I discuss them again and then relate with those graphs the variation of velocity during the simple harmonic motion. XT graphs, which means displacement time graphs, could be represented either in this manner, which means that the object is initially at extreme position. That means it is already at some non-zero value of displacement, and that is the maximum during its oscillation. So maximum displacement during the oscillation is amplitude. That means if we have a graph of this type, we readily understand what is the amplitude of the oscillation. The equation that governs this type of change is x is equal to x naught cos omega t. We discussed this equation yesterday, and I emphasized that cos omega t, if t is 0, that means we are here initially, we have just started our stopwatch, and the oscillation are going on at that time. The object must be at the extreme position then, because cos omega t will have value equal to 1, because omega t 0 means cos 0, and that is 1. So x will come out to be equal to x naught. That means the object is at that particular instant at the extreme position. But as we continue observing it, it moves from this extreme to this extreme. Before it comes to the other extreme, it passes through the mean position, goes to the opposite extreme position, then passes through the mean position, and then comes to the same position where it started. So this is the sinusoidal variation, which is used to describe the variation. But side by side, it's also important that we understand what is the equation we use when the object is at mean position initially, and this is what the subsequent variation of it. If it is initially at the mean position when we start our stopwatch and observe its subsequent motion, the equation that we use to describe this variation is x is equal to x naught sine omega t. So this point we discussed yesterday. Sine omega t, if it is 0 initially, because t 0 makes omega t 0, which means angle 0, which means sine 0 is equal to 0. That means initial value of x must be 0. That means when we started our observation, the object was at the mean position, and then as the time goes on, the value of angle goes on changing. This becomes pi by 2, then pi, then 3 pi by 2, then pi. So these values goes on changing, and the value of displacement varies, which means the object is at the mean position, it goes to the extreme position, then it goes back to the mean position, goes to the other extreme position, and then back to the same point where it started. We need to understand what is the relationship of velocity at various positions during the oscillation. So VT graph, that means we have V on this axis and t along this axis. If for this particular situation I want to know what should be the Vt graph, it could be something like this. Which means when I observed the object at the extreme position, it was not moving at all. So initially, the object is at rest. But when it is at the positive x side, when the object having passed through the mean position go to the other extreme, it has the large value minus x naught now, because it has gone on this extreme, the left extreme. The value of x naught is now negative. I mean, this value will be minus x naught, but the value of velocity has fallen to 0 now. Now this position is the point which correspond to this, because when it is on the extreme position, it should not be moving. For a moment it comes to rest, and then it continues and passes through the mean position again, and then its velocity is maximum again, and it becomes positive this time because it is rushing towards the positive x direction. So at extreme position, the object comes to rest, so V should appear 0. When it is rushing towards the negative side, it is minus V naught, the maximum velocity. When it is at the other extreme, the negative x direction, it is coming to rest for a moment, and when the object moves to the mean position again, it has the maximum velocity. And then finally, when it goes to the right extreme, the object comes to 0 again. So while it completes its motion here exactly during taking t as the time period, exactly during this time, the object has completed this cycle, starting from rest and coming to rest between the two extremes, taking the round trip. Similarly, if I make a VT graph of this situation in which the object is initially at rest, we can see, it's easy to see that this time the graph will look like this. Because when it at the mean position, the object will have maximum velocity. When it goes to the extreme position, its value drops to 0. When it comes back to the mean position, its value become minus V naught to the rushing towards this side, and then it continues to be 0 because it has gone to the other extreme position. And when again it comes to the mean position, it has maximum value again. So same situation is here. In same time period in which the object has completed one round trip, like in these two positions, between these two positions, during the same time, it has completed this cycle on the velocity time graph. So we need to understand how to interpret where exactly is the object is at rest on the graph, and where it is moving towards right, where it is moving towards left, the significance of positive and negative signs. So I have tried to explain it in quite a detail. But when you attempt on your own, you will see this in the questions, and we can have more of this discussion when we try a few problems together. One more formula that we we're going to discuss now is the variation of velocity with position. Instead of dependence of velocity on time, we are going to see how velocity varies with position. This formula, let me for one last time state quickly what this relationship means. This formula clearly states that we know at certain particular instant given in the question, we might be asked to know what is the displacement of that object, what is its amplitude, what is its frequency, what is its time period. Because omega is 2 pi f, so we can quickly calculate the frequency of any such object which is undergoing simple harmonic motion. So this equation or any other given, they can be used to describe it in full detail, making these simple calculations and interpreting what is going on. So it is the relationship between displacement, velocity, and time in all these graphs. Variation of velocity, with position. And that is given by plus minus omega x naught square minus x square under root. This equation, which of course is a solution of a certain equation that is beyond the scope of your syllabus, this formula needs to be recalled to solve various problems. That means you need to memorize it, you need to practice this and understand the significance of each term in this formula. But we do not have to derive it, we do not have to the derivation from the second order differential equation. So that is not something we have to worry about. This is velocity at any position, as the symbol V is suggesting. Omega has the same meaning. We have been using it. Angular frequency, which means it could be 2 pi f or it could be 2 pi over t. That means if time period of the oscillation or frequency of the oscillation is given, that means we know the value of omega. This x naught is the extreme position, which means this is the amplitude of oscillation. And this x is any position, any instantaneous position, any momentary value of the displacement x during the oscillation. So there may be situations in which they ask you to calculate the maximum velocity or the velocity at any position x. Let's first see what the maximum velocity is from this expression. Clearly, maximum velocity is at the mean position. And at the mean position, the value of x is taken 0. That means Vmax should always be calculated using plus minus omega x naught square minus 0 under root. And if you simplify it, this 0 goes and this gets cancelled with the root sign. So plus minus omega x naught. This is always the maximum velocity of an object executing simple harmonic motion That means if you know the frequency given and if you know the amplitude of that oscillation, you can calculate the value of maximum velocity. Let's discuss an example of such a situation. Suppose it's a cone of a speaker. You know, the cone of speaker undergoes simple harmonic oscillations when it is attached to loudspeaker. It produces a loud sound because the vibrations enhance this effect. The vibrations have certain frequency and it is given to be 1400 hertz. The cone of the loudspeaker is having this frequency, and its amplitude x naught is given by value something like 0.08 millimeter. So with these values, we want to calculate the maximum velocity with which the object, the cone of that loudspeaker, moves. Obviously, the maximum velocity will be achieved when that cone is moving from its mean position, and at the extreme position it will come to rest. At this extreme it will come to rest. So at the mean position, V max must be equal to 2 pi f, which is omega, and then x naught. So this is the maximum velocity with plus minus sign, which simply means it is either moving to the positive x direction or the negative x direction. If I consider just the magnitude, naturally I can ignore the signs, and if I use these values 2, 3.14, 1400 and 0.08 into 10 to the power minus 3, all this simplifies to a number something like 0.70 meter per second. This is the kind of velocity which is maximum if we have this velocity. This is the value of frequency and this is the amplitude of that system. They might ask you, in fact, in this same question, which appears in October-November 5, it's an old paper in which this question appears, but in recent exam papers, you might have questions like this. What is the maximum acceleration of the same object? For maximum acceleration, you go back and recall the equation A. This is A max. Let's see what A max comes out to be. For A max, you need to remember minus omega square x, which is the general equation, the characteristic equation of simple harmonic motion. We can ignore this negative sign because the purpose is to calculate the maximum value of acceleration. So we can ignore the negative sign and use the maximum value of displacement here. That means acceleration will be maximum if I replace the value of x with the value of amplitude. So using the same values given in this question, if I use 2 pi f whole square multiplied by the same amplitude we have used already, 10 to the power minus 3, it comes out to be approximately 6,200 meter per second square. So if we know the values, it's easy to calculate the maximum acceleration, the maximum velocity. That means in relations like this, we just have to, we just need a couple of values to calculate the maximum values. But what if it is not maximum value, it is any other value at a certain position? Let's try to calculate that velocity as well. Suppose an object is undergoing simple harmonic motion. This is its mean position, and this is one extreme position, and this is the other. So an object undergoes a simple harmonic motion between these two extremes. So that means this is its amplitude, and suppose this is exactly equal to 4 centimeters. So from the mean position to one extreme, it is 4 centimeter, and let's assume it has a reasonable frequency of nearly 50 hertz. We want to know what is its velocity when it is 2 centimeter from the mean position. Suppose it is here, exactly midway between the mean position and one of the extremes. So this is the position where it is 2 centimeter from its mean position. So value of x is given to be 2 centimeters, and x naught is already known, this is 4 centimeters. So we want to calculate the value of v with this set of values given. Using this formula, it is easy to see that 2 pi f, which is omega, and x naught is 4, which is squared, and minus 2, which is also squared, and this is under root. Using the rest of the values, 2 into 3.14 into 50, and this is 4 square, that means 16 minus 4 under root. And this of course simplifies to a certain number, but before that take care of the units. This must be 0.04 meter, and this is also 0.04 meter. So with this we need to change this, and it must be 0.04 square minus 0.02 square. So you need to simplify all this. Whatever number you have here, you multiply it, and it's a simple calculation which gives you the value in meter per second. That means if we know the amplitude, that means it is 4 centimeter in this case. We know a particular value of position given, which is this must be 0.02 meter, because this was 2 centimeter. So at 2 centimeter, if I simplify this, I know what is its velocity at 2 centimeter. The maximum velocity can also be worked out for such a system, and V max, once more, it is omega, if I ignore plus minus sign, multiplied by x naught. This gives us the maximum velocity. So we can have the value of maximum velocity, we can have the velocity at any position x, and this is how we can work out velocity at any position. One more thing, and that is the variation of kinetic energy. Because this expression gives us the variation of velocity with position, we can derive an expression of kinetic energy with position. Kinetic energy, which is of course a variable because its velocity is not same, it continues varying. So kinetic energy is also a variable. So using that standard expression for kinetic energy and using this V as plus minus omega x naught square minus x square, we can have an expression 1/2 m omega square x naught square minus x square. So this is kinetic energy at any position x during its oscillation, which means one more thing that I need to know is the mass of the object. The remaining quantities are same as I discussed in this case. In V, we of course do not require the mass. We can calculate velocity without worrying about its mass, but in order to calculate kinetic energy, we have to add the value of mass as well in the expression. And this is a very, very simple expression that tells us how kinetic energy is varying with displacement. Graphically, it is represented if I take energy along the vertical axis and displacement along the horizontal, kinetic energy varies in this manner. And this is the graph that we'll use in the coming lessons. There are many questions in the exam in which we have to use this graph and calculate many unknown quantities with energy known, and with the help of this energy known, with the help of the amplitude of the oscillation known, we can calculate so many things related to it. So I stop here with this kinetic energy at various positions during the oscillation. We'll have potential energy in the next lesson and the total energy, and that will complete most of our discussion of the oscillation. Thank you.